All right, so today we're going to do a little more integration by parts. My guess is that I'm going to finish up by 2, maybe 2:15. So we might cut out a little early today. Just remind me because I might just get going and lose track of time. So I've
office hours aren't going to go back to normal
till next Tuesday. Tuesday, yeah.
This coming Tuesday or Tuesday?
Well, this upcoming Tuesday, yeah. Yeah, it's just tomorrow and Monday. I'm not going to be here.
What time do you normally get?
Usually I'm in there by around 9. Usually around 8:30, but I'll say 9. Yeah, and then all the way till 1. Okay, so I have done the videos for the homework problems 1 through 25 are on the web. I just finished doing 26, 27, 28, 29, and 30. I haven't posted them to the web yet. So hopefully by the end of the day, all the problems for the homework for integration by parts will be posted. So because of that, I don't plan on entertaining any questions over the homework problems because there are videos for each one, right? So we did not finish the notes from last time, did we? We did not. So I would like to finish those. And we were working on problem F. I was going to do a quiz today, and this was going to be the quiz. Take out your integration by parts homework, and I'm going to come around and take a look at it. I wanted to see where you were, like how far you had gone. So if you wouldn't have had any homework, you would have had a 0. If you would have had some of it, then I would have scaled it up. If you would have had most of it, then 100. So just be prepared for that, because I plan on doing that probably on Tuesday. I need to make sure you're keeping up with your homework. I figured I'd give you the weekend, you know, and that way you can watch football and do calculus. Okay. All right, so here we go. Integral sine to the n of x dx. So n here is an integer, all right? See, we don't know what the power on the sine function is. So look at the instructions here, if you have your notes. It says, creating a reduction formula using integration by parts. So what I'd like to do is refer to you, get your formula sheets out. Where's my formula sheet? There it is. I'd like for you to look on your formula sheets. Do I need to have a quiz on whether or not you brought your formula sheet? Should I have a quiz on that too? All right, so let's say on Tuesday I'll check your homework and your formula sheets. And that'll be your one time. If you miss it Tuesday, if you don't have it, you get a 0 on the quiz. If I check it again and you don't have it, you don't get to use it on the test. All right? So have it. Okay, so on this formula sheet, what is that? Extra homework? Okay, on this formula sheet, notice that they stop at 29, right? What do you look for? Go ahead. All these formulas stop at 29. I mean, all the formulas we stop at 29. I said in the book there's more, right? So on the formula sheets, do you see anything that has sine to the n power? There's really only, just number 6 has sine and that's it, right? We all know the antiderivative of sine. But there's nothing that says sine to the n power. But if you were to continue to look in the other formulas that you don't have, that you're not allowed to use on the test, there is formula 73 in the book. And let me write it down here for you. All right? It is sine to the n of x dx equals, all right, negative 1 over n sine to the n minus 1 of x cosine x plus n minus 1 over n integral sine to the n minus 2 x dx. Let me just double check that I had that right. Negative 1 over n sine to the n minus, that's n minus 1 power right here. Cosine x n minus 1 over n sine. Okay, that's it. Right, this is what we call a reduction formula. So let's try and understand how a reduction formula works. This says that if you want to integrate sine to a power, n, that you can turn it into this, and notice that this is just sine and cosine in here. This is a new integral, right? This new integral is different from the original integral in the sense that the power on it has what? Come down by 2. And so what you've done is you've taken sine to maybe like the 4th power, and now you've turned it into sine to the 2nd power. Understand? This formula allows you to take high powers of sine and break them down to a new integral. Does that kind of make sense? So let's just set up a problem, and then we're actually going to prove the formula. We're actually going to come up with the formula ourselves. All right? But for now, let's see how the formula works. So let me just change this problem right here. Sine, how bad do I want to go? Let's go sine to the 5th. Sine to the 5th power. According to this formula, this is equal to what? Negative 1 over 5 sine to the 4th of x cosine x plus 4/5 integral sine to the 3rd x dx. Right? So we've taken a problem that was originally sine to the 5th power, and according to this formula, it's now, we just have to be able to figure out what sine to the 3rd power is. So what should we do? Do the formula again, right? How about the formula just on this piece? So I say this is equal to negative 1/5 sine to the 4th x cosine x plus 4/5 times, now big bracket here. This is where I'm saying I have my bracket. This right here is this formula again. This time n is being 3. Understand? So it would become what? Negative 1/3 sine what? Squared, sine squared x cosine x plus, remember n is 3, right? So 2/3 integral just sine. Ah. Will I need to apply the formula again? No, because I know what the antiderivative of sine is. You see that? So this reduction formula allows you to take high powers and break it down, break it down, break it down, break it down until you get to something you can handle. Yes?
I just want to make sure that until you get rid of the last integral, you don't have to put it plus c, right?
That's right. Until you actually do the integration is when you could throw the plus c on there.
Because right now all we're doing is with c.
Yep. So the answer here, I would just replace this with what? Negative cosine x, right? And then I would say plus c, right? And this would be your answer. You would have to distribute the 4/5 through, and that 2/3 would be in front of the cosine. So I'm not going to go any further, but you see how convenient and useful that is? You see that? Now, let's come up with a formula. This is going to be the hard part. Most of the time, reduction formulas, which is what I'm about to do, any time that I've ever asked a question on a test about a reduction formula, it's normally appeared in the form of a bonus question, because these are not very simple. They take some time. All right, let's go back to this. Okay, here we go. How do we come up with that formula? So this is not a very natural thing that I'm about to do, all right? But just tell me if you agree with this. First, I'm only going to be looking if n is greater than or equal to 2. Because if n is 1, do we even need a formula? No. And we're going to find out later today, if I have time, that if n is 2, we actually don't need a formula either. But n3 and higher, usually you want to try and have a reduction formula. So let's assume first n is an integer that's bigger than or equal to negative 2. All right, so do you agree that I could do this? I don't know what I'm doing there. I'm going to set up integration by parts table. Let me set up my table. I'm going to choose a u and a dv. But right now, I only really have one choice of u, right, Luke? What's my only choice of u right now? Sine to the n of x, right? That's really my only choice, and that forces me dv to be dx. If you do that, you're going to go nowhere. All right, it's not going to happen for you. So I'm going to do something tricky. I'm going to rewrite the integral. I'll put n is greater than or equal to 2 up here. I'm going to rewrite this integral like this. Do we agree that that's the same thing? I don't like the way I'm putting these powers in here, n minus 1. Is that the same thing? What's the power on this sign? 1. And the power on this sign? N minus 1. What happens if you have the same base and you multiply together? What do you do to the exponents? You add them. N minus 1 plus 1 is n. So that's the same expression, right? Now, why would you ever do that? Okay, that's what makes these hard, right? Is why would you ever do that? So if I do this, okay, if I do, let's see what happens if I let this be my u and this be my dv. So let's let this be sine n minus 1 of x is my u, and then dv is sine x dx. It's not obvious right now that this is going to get us anywhere, but let's see. So let's see. Is it too much to call on someone for this? Who wants to be called on? Someone hasn't been called on. Okay, go ahead, Luke. Give me the derivative of this.
It would be sine n minus 2
Okay.
x.
All right. Sine n minus 2 of x dx. Right? So what, you just reduce the power? There's still more here, though. Remember, the power has to come out, right, when you're taking a derivative. N minus 1 out front, there's still something missing. Chain rule. Right? So n minus 1 is like a power. Look, sine of x to the n minus 1 is what we have, right? That's what that really means. When we take the derivative, the n minus 1 comes out. Then you subtract 1 from that. And minus 1 is minus 2. Then the derivative of what's inside, which would be?
It should be cosine, not sine.
What's that?
It should be
Well, no, because I still need to take the, that's not correct. But that's why I'm going through it. N minus 1 comes out, right? So the derivative of this is n minus 1 comes out. Now it's sine, take the power down by 1, n minus 2 of x. Now the derivative of what's inside? Cosine x dx. That's du. Got it? So let me come back over here. Du equals, I don't have enough room here, so I'm going to go du equals, then n minus 1 sine to the n minus 2x cosine x dx. Y'all with me? Yes? Okay. The next thing is to integrate up the other side. So v is what? Negative cosine x. Yes? All right. So this integral is now, we are going to use that acronym. Justin, what's that acronym? It's not really an acronym, but what's that little thing that I've been using? UV minus voodoo, right? Ultraviolet minus voodoo. Okay, so ultraviolet, these two multiplied, right? Yes? Those two multiplied is negative sine to the n minus 1 of x cosine x minus the integral of voodoo. And voodoo is this, right? Voodoo is this. So what would we get here? Do we have any constants we can pull out? n minus 1 and a negative, right? So negative and an n minus 1. So why don't I pull that out? I'm actually going to write it like this. I need a little more space. It's going to be plus n minus 1 integral. Now, what's still in there? Cosine squared and sine to the n minus 1. So I'm going to write it this way. Sorry, I said sine n minus 1. Sine n minus 2x cosine squared x, right? dx. Y'all with me? Anyone have any issues with this? Follow? All right, is that the formula? Look at the, well, if you wrote it down, hopefully you wrote it down. Did our formula, was the first piece sine to the n minus 1x cosine x? Did it have those in it? Yes? But it had something else out here, didn't it? It was negative 1 over n? We don't have that yet. Okay, how about that other integral, or the other part of it? Was there an n minus 1 in it? Yes, but it was divided by n. Was it plus or minus? It was plus, so it's starting to look like the formula, isn't it? Over here, what did we have in this one? In the integral? Sine to the n minus 2x, right? But no cosine squared. So it looks like we're starting to get to something, right? We're starting to, but we're actually not there yet. All right, so let's continue. What I'm going to do now is I'm going to work with this. I want everyone to tell me what this is from pre-cal. It's 1 minus sine squared x, isn't it? Isn't that 1 minus sine squared x? So if I rewrite this entire line, negative sine n minus 1x cosine x plus n minus 1 integral sine to the n minus 2x 1 minus sine squared x dx, right? Then that's just replacing that with 1 minus sine squared. And then what would happen if you distribute this through here and here? So what's sine to the n minus 2 of x times 1? Itself, right? What's sine to the n minus 2 of x times that? Sine to the n, right? You add the exponents? Sine to the n. Okay, so let's see what happens here. This equals negative sine to the n minus 1x cosine x plus n minus 1 integral of sine to the n minus 2x minus sine to the what did you say? nx dx. Agreed? All right. Anybody see it? Anybody see it? Anybody see it? What is this? What is the integral of this? It's the original thing. Didn't this happen before? When the thing we were trying to solve for appeared over here? And what do? We moved it back over here. This was the rabbit out of the hat one. Right? So the integral we want actually is over here. So we're going to need to get it and move it to the other side. But to do that, we have to first release it from, right now it's being, you can almost look at this n minus 1 as being a scalar out in front of this, right? So what I'm going to need to do is I'm going to split this into two separate integrals, distribute an n minus 1 through to each one, and then move that one over. Okay? That's what I'm going to do. All right, so now my next line. So what I'm going to do, I'm going to keep this is the original problem. I'm going to rewrite this line right here. Okay, this is where we were, right there. Okay, and this is negative sine to the n minus 1 x cosine x plus n minus 1 integral sine to the n minus 2 x dx minus n minus 1 integral sine to the nx dx. Robert, do you see this? Do you see what I did here? You see the n minus 1 has to go to both? Okay. So I have a minus sign there. So now, let's see. I'm going to add that to both sides, right? This. So how many of them do I add? Yeah, what's the number out in front of it? N minus 1. So I'm going to add n minus 1 of these integrals, right? Like if that were a minus 4, I'd be adding 4, right? Same thing over here. I have to do this to this side. Going to add n minus 1 of these integrals. Right? That's what I'm going to do. It'll cancel on this side. Alexis, how many of these do I have now? How many of them are here? That's how many are here. How many are here? One of them, right? If I take one of these and I add n minus 1 of them, how many do I have? N of them, right? And I'm going to divide by n. Yep. So when I add these two together, I'm really adding these almost like coefficients. Like 1x plus 5x is 6x. But when you add these two together, the ones cancel and you just have the n. So we're actually really close to being there. I have n of these integrals is equal to negative sine n minus 1 of x cosine x plus n minus 1 integral sine to the n minus 2x, right? That's what I've got. And Ron, the last thing, right, you said? Divide everything through by n, right? Just divide by n now. Divide by n, we divide this by n, we divide this by n. So let's do that. Divide this by n, divide this by n. I don't know, divide the whole thing by n. Divide this one by n, I'll put it right there. And you'll get what? Integral sine to the nx dx equals. Now, I could just leave this, right, like this all over n. But I could also write it like this, negative 1 over n, couldn't I? Sine to the n minus 1x cosine x. I mean, that's the same thing, right? That's the same thing. And then over here, plus n minus 1 over n integral sine to the n minus 2x dx. That's it. That's the formula. If that doesn't get you excited, nothing in this class is going to get you excited. I'm kidding. So when you go and you flip to the back of this book and you look at these formulas that they have here, you know, and you go, where do these come from? You know? It wasn't, no, I better just shut up. I won't go there. I don't want to get political or religious in here. So I will just say that These were not provided to us by any divine power. These formulas came from people who ground them out, right? Had to come up with these. And that's an example of how something that looks pretty ugly, it's doable, right? I mean, there's a little bit of magic in there where how did they know to write that first one to break it up? But I'll tell you how they knew. Someone really wanted to solve that problem, and they just kept beating it to death and trying over and over and over, different things, and finally got something to work. And that's the way a lot of mathematics works. You get these nice, elegant results. You don't realize there's like years and years of pain and suffering that's behind that someone found that. So we just get to reap the benefits of getting to use it. Okay, so that is an example of proving a reduction formula. And there are, I believe, a few of those on your homework. Did I give you those for homework? Let me see. I believe I assigned number all the way up to number 32, right?
35 and 37.
Okay, so, and 31, right? 31. Number 31, number 32, number 35, and number 37 are all reduction formulas. And I challenge you to do those. I did not do a video on those. In my video that I did do, I told you I'm not going to do the reduction formula ones because those are usually bonus problems on a test. So there's a very good chance that one of the problems that I'm asking you for homework will appear as a bonus on the test. I'm just not going to work it out for you. At least you know the answer, right? You'll know what the answer is because it tells you show this is true. So you'll know what you need to get to. It's a matter of getting there.
So you'd be giving this in the questions?
I'd say prove this. Yep. And then you'd have to do all the work I just did. All right, well, what I've decided to do, all right, is I've decided that due to the quizzes, which were pretty good, okay, the quizzes, there was a good chunk, I'd say 80% of the class got perfect score on that quiz that I gave last time. I feel like hopefully everyone's kind of keeping up to speed. I'm going to give you the weekend to really get that integration by parts down. And then we're supposed to come back and have what? Our test is next Thursday, right? So we're supposed to come back. Wait, no. Yeah, is it? Yeah. We're supposed to come back and do a review, right? What I've decided to do is to introduce you to this concept and put maybe one or two of these on the test. Now, the reason why is because these, I think, are a lot cleaner and easier than an integration by parts. So when you see these will actually be kind of, you might be like, good. You know, like, I feel comfortable with these. Because there's really only so many things you can do with these sorts of integrals. All right? So we'll look at that for the next half hour, 45 minutes. All right, 6.2 is called trigonometric integrals. Didn't I promise you I was going to let you all work together? Like work? Sorry, I lied. So trig integrals and substitutions. This section has two major concepts in it. Trig integrals, which are integrals that have trig functions in them, and then what are called trigonometric substitutions, which are integrals that do not have trig stuff in them, but we turn them into things with trig stuff in them. That's a much more difficult concept. All I'm going to do is work on the first part of this section, which is trigonometric integrals. So we have seen already, we know the antiderivative of sine and cosine, right? We also talked about last class that if you had a linear expression inside of a trig function, right, that we always have to scale by it when we integrate it, all right, but by the a. And now what we're going to look at is a strategy for integrals that have sines and cosines in the integral together. Not just a sine by itself, not just a cosine by itself, but sines and cosines combined. And have some sort of like general attack or strategy for those. So here's the first strategy. And there are 1, 2, 3 strategies for when you have cosine and sines together. Right? The first strategy says if you have cosine to the n power in your integrand and the n is odd, then we're going to use a Pythagorean identity. then we're going to do blah, blah, blah. I'm not going to read through this. When I do an example, you'll see, I'll show you what I mean by all these words, okay? But it's like if the power on the cosine is odd, we're going to try this. If the power on the sine is odd, we're going to try something else. And if you have the power on sine or the cosine being even, we're going to try something else. All right? So those are the things we're going to go for, and here's the first example. So let's do that first one, A. We're going to have integral sine cubed 4t dt. Now, I will point out, or I will ask you, Kiki, can you use the reduction formula we just proved on that? I mean, but do you think it falls into that format? What's the n here for us? 3. And so in that reduction formula, the new integral, wasn't it n minus 2? So if we take 2 away from that, it would just be sine in that new integral, wouldn't it? And we can do that, right? So the reduction formula would work very clean on this, wouldn't it? But let's try something to get us used to this new strategy, because if I throw like a cosine squared in here, it's all going to go crazy. You won't be able to use that reduction formula. So according to this, if I have sines and cosines, and my cosine is odd, I do the first thing. But I don't have cosine odd, right? I have the second thing, which is sine is odd. So let's see what this says. If sine is odd, here's what I'm going to do. I'm going to use the Pythagorean identity. What I'm referring to here is this identity. Remember that from pre-cal? I'm going to use that identity. I'm going to factor out a single factor of sine. So I'm going to come to my integral. I'm going to rewrite it. I'm going to factor out a single factor of sine. So I had 3 factors of sine. It was odd. So I'm factoring a single factor out. Everyone agrees that's the same thing? Come on, Kiki.
I'm trying not to die. Sorry. I'm dying.
Yeah, if you're going to die, please don't bother us while you're dying over there, okay?
I'll try not to put anything in the future.
Please. Thank you. All right, so once we do that, what? We pull out a single factor. What does it say? Which leaves an even power of sine, doesn't it? Like if this was odd, and I pull out one sine, I'm guaranteed that this is going to be even, right? If that was 5, I pull out one sine, I'll have sine to the 4th here. So no matter what, this should work. Now what do I do with that even power of sine? Rewrite the remaining even power of sine using this substitution. So remember that with this identity, I can always move things around here. So I can just rearrange this sine squared x equals 1 minus cosine squared x, right? I'm allowed to do that. So everywhere I see a sine squared of something, I can replace it with the 1 minus cosine squared of that something. So I'm going to replace this right here with 2 terms. And since there's 2 terms, I need a parentheses. 1 minus cosine squared, Kelly, of cosine 4t. There we go. And then the rest of it, the sine 4t dt. Now, without looking too far ahead, let's see. Matthew? Why in the world would I do something like this? Think back, Matthew, to when the first technique of integration we ever learned, right, was what? I mean, other than after the power rule, we learned the basic substitution, right? Look at this right here. And go back to the good old days when it was just, do I see something in a derivative?
Yeah.
You see something as derivative? What do you see? Either way, right? If we let this be u, the derivative of it's there. If we let that be u, the derivative of it's here. Which is better? You want to use the one in here. The reason being, because the derivative of it needs to be free from the other stuff. If you let u be sine, then the derivative is in here and it's squared and it's 1 minus and it's in parentheses. You don't want that. You want it free. So this is a pretty good candidate for a u substitution, isn't it? Just a basic one. And that's what this technique tells you. Okay, you've done all the stuff it told you to do. Now, just let u be cosine x and use substitution. So now what I'm going to do is I'm going to make a substitution in the problem. Everywhere I see u, I'll replace it with cosine, now not x, what here for us? 4t. And then now I just go through the basic substitution. The derivative of this is 4 sine 4t dt. Because of chain rule, right? You have to take derivative of what's inside, and so we're off by 4. And so do we have this? Does this appear in our integral? Almost, right? Almost. We've got sine 4t dt. Sine 4t dt. So we're off by a factor of 4, aren't we?
Is that going to be negative?
Yeah, why didn't I put negative? Is that why y'all were all looking at like that? That's the second time you caught me, Karen, right? You caught me on another one that I left out over here. Remember that a couple of classes ago?
So u is not going to be the 1 minus cosine?
Doesn't need to be. Nope. You actually, if you did that, your derivative would be more complicated because you would have to use the chain rule. So the 2 would have to come out. Like if that were cosine squared, 2 would have to come out. Then you would still have cosine. Then the derivative of cosine is negative sine. So it would be kind of messy.
Why would you use 1 minus cosine?
That's what I'm saying. Watch. If I do this.
I'm not saying you squared, but do you have to take it?
Oh yeah, no, you can't because that's not there. This is not here. The order of operations, excuse me, says you have to square this before you can combine these together. So you can't let u be something that would change the order of operations. Like how would you rewrite that? If you're calling 1 minus cosine 4t u, then how would you rewrite this here?
Well, it's because the squared isn't on the outside.
Yeah, if the square were out here, then yes. You following me?
Yes.
Okay. Okay, so the derivative of cosine is negative sine, chain rule, negative 4. So I need to scale by that. So negative 1/4 du is equal to sine 4t dt. Any questions? All right. Paul, you feeling good today? All right, you want to tell me how I can rewrite this integral in terms of u? Can you see it okay? All right, so I'm going to do it up here. How could I rewrite that integral in terms of u? 1 minus u squared, good. And then what's all this? Okay, I'm going to pull the negative 1/4 out here. Du. Good, right? And what's good about that integral? It's so easy, right? This is just basic power rule. What's the antiderivative of 1? U, right? And what's the antiderivative of u squared? 1/3 u cubed. That's it. We're done. And then we have the negative 1/4 out there also. But do you see how that became very clean after we made the substitution? So 1/4 antiderivative of each one. So antiderivative of 1 is u. Antiderivative of u squared, negative 1/3 u cubed, plus a constant. All right, Dustin, feeling good? You want to give me what the answer is, distribute the negative 1/4 through, and replace everything with u. See if you can walk me through what this next line would be. U with what was u? Okay.
cosine, or negative,
Uh-huh.
cosine 14.
Don't forget, do.
So positive 1, 12.
Yep. So cosine cubed 4t. Right? That's u. U is cosine. And when we cube it, we like to put the cube there. That's the notation we use. And then plus c. We good? It's a little better than integration by parts. Right? Another thing about these is that as soon as you see them, you kind of know what you have to do. Are there any questions on this? You got a question?
Okay, so when, since it was negative cosine 4t as u, wouldn't that change the signs on both of those?
The u was not negative cosine. It was just cosine. The derivative was negative sine. Zach, remember you were skeptical about these last class because like how could the derivative of this possibly be that? On the videos I did a few, I think 2 or 3 just for you, Zach, just to show you that the derivative did work out. So I'll do it on this one quickly, all right? So what is the derivative of that right here? Let's see, negative sine of 4t times 4, right? Negative sine. So what happens when that negative 4 comes out and hits this? You just get what? Sine 4t? That's what you would get when you take derivative of that? Okay. Here, bring the 3 out. I'll do this one a little slower. 3 comes out, it becomes what? 3 over 12 is 1/4. Cosine what? Squared of 4t. Now you have to take derivative of cosine, which is negative sine of 4t. But then you have to take derivative of what's inside, which was what? 4? This 4 and this 4 cancel? Yes? Y'all agree with this? So what do we have here? Is there anything I can do with this? Can I factor out? How about if I factor out? Let me see. I'll rewrite it so it'll look a little more obvious to you. So I just took that negative and slid it out in front. What can you do here? Factor out a sine 4t. If you do that, what's left? 1 minus cosine squared 4t. But what's 1 minus cosine squared 4t rewritten? It's sine squared 4t. And so you have sine 4t times sine squared 4t, which is sine cubed 4t, which is the original integrand. It worked. Okay. Let's try another one. So for part B, we have integral sine squared x cosine to the 5th x dx. Are we allowed to do exactly the same thing we just did? No, right? Because what we just did is when you have an odd power on sine, right? We can't use the reduction formula that we proved at the beginning of class because that only works if it's just sine by itself, right? So whenever we have sines and cosines combined, we look at these 3 possibilities. And the second one, no, the first one, sorry, the first case is what you do when you have cosine having the odd power, which we have here, right? So what does it say for us to do? Use the Pythagorean identity again, but this time we're going to factor out what? A single factor of what? Cosine instead of sine. So I'm going to rewrite this. X, hold on. Cosine, yes, this one right here. And then I pulled, sorry. Dropped the ball on that one, sorry. Fourth. And then cosine x dx. So I just left sine squared alone. Cosine to the fifth, I rewrote as cosine to the fourth times cosine. This time I'm going to use a Pythagorean identity, but the other way. Instead of using this, right, that's what I used for the last one. Everywhere I saw sine squared, I replaced it with this. Instead, I'm going to use this version, which is the Pythagorean identity solved for cosine squared instead of sine squared. And so everywhere I see a cosine squared, I'm going to replace it with this. Okay? But I don't have cosine squared. I have cosine to the fourth.
Cosine squared plus cosine squared.
That's cosine squared times cosine squared, right? Even better, could I write it like this? Sine squared x times yeah, I'll do it this way. Cosine squared x squared cosine x dx. Do you agree that cosine to the fourth x is cosine squared x squared? Yeah? And now this becomes integral sine squared x in parentheses and squared what? 1 minus sine squared x, and then cosine x dx. Ivana? The whole purpose of that is because now you look at this and you see what? How do you mean factor it out? What I'm trying to ask you is what technique of integration do you see we could use? Just a basic substitution, right? Just a basic substitution here. Because if I let u be what? Sine x, the derivative of it is right there. Sitting there waiting, nice and patient, right? And that's what the step even tells you that at the very end. It says let u be sine x. So these little hints actually tell you exactly what you should use for u. So now I let u be equal to sine x. Du is cosine x dx. And I rewrite the entire integral. And let's see. Who have I not called on? Anyone here want to do it? I know I've called on yo too many times already. Go ahead, Christy. I don't call on you now. Just rewrite this integral with that substitution. U squared 1 minus u squared squared du. Right? Everything just goes clean into it. That's du. This is 1 minus u squared, but then all that's squared, and then this is just u squared. How are we going to do this, Sean? Or how would you do this, I should say, Sean? At this point, it should be simplified. Like you shouldn't need anything crazy now.
Will you take out the u squared? Just one or?
Out here,
Yeah.
be careful. You can never take a variable that's part of your integrand, right? The variable can never come out. You can always pull constants out, but you can never pull the variable itself out. Anyone? Yes?
Separate the squared to 1 minus u squared.
Just square it, right? Just square it. If you square that, you get a bunch of powers of u, don't you? Then you just distribute a u squared through, and then you just get a bunch of powers of u, and then you just do power rule on each one. So at this point, it's just some algebra to clean it up. You don't have to use any crazy other techniques. So this is integral u squared. When I square this, I get 1 minus 2u squared plus u to the 4th du. So I'm just doing that mentally. This times itself, FOIL it out, collect like terms, you get that. Agree? And now just distribute the u squared through. I'll have 3 terms. U squared minus 2u to the 4th plus u to the 6th du. Alejandro, you want this? Not really? Just apply your power rule to each one. I'll put this in.
It's going to be 1/3.
Oh, no more integral, sorry. Yeah, 1/3.
U to the 3rd power.
Uh-huh.
N minus, is that 2/5?
2/5.
U to the 5th power.
Uh-huh.
Plus 1/7 U to the 7th
Yep.
power. And plus 2.
That's it. And final step, replace all your u's with sine x. So this should be 1/3. It's sine x, but then being cubed, so I'll put 3 here. Then it's minus 2/5. And then it's sine x, but then raised to the 5th. And then plus 1/7, and then sine x to the 7th plus c. That's it. I won't check this, Zach, sorry. Not going to do it. What I think is worth mentioning to you is that if you go to Wolfram Alpha and you say integrate, what was it, sine x squared times cosine x, was it to the 5th? Yes? Okay, if you ask Wolfram Alpha to integrate this, oh, wow. Did we mess up? No, it's just that Wolfram Alpha did additional things. What they did is they said, okay, I'm going to use some power reducing formulas on this. Because notice your angles have changed there. They have a sine cubed x in there, don't they? But they've got a bunch of other stuff. They've got a cosine 2x. Do we have a cosine 2x in here? Somehow they changed things into double angle formulas, and they actually have a cosine 4x, so they applied double angle twice. So I always know, like on a test, when students use like their TI-89, things like that, because your calculator is going to do more than you would do. You would stop here. So if your answer has like cosine 2x, you obviously didn't do it, right? Because to get it to look like that is about another 30 minutes of work. But this is correct. This is a correct antiderivative. That's just identities to get it to look like that. So be careful. All right, that's fun. You want to do another one? This will be our last one. Cosine to the 4th x. This is sometimes referred to, in my mind, beta t, sorry. Cosine to the 4th beta t dt. In my mind, this is considered to be, an instructor that puts a problem like this on a test, it's considered to be torture, okay? Because this is very tedious, this problem right here. Now, there is a formula that we could use in the back of the book. You know how we had one for sine to the n? There's one for cosine to the n. But let's try not to use that formula because you can't use that on your test. Let's try and do it using technique here. So remember, the first two little techniques were what you did if cosine was odd or sine was odd, right? The third one, which we haven't discussed, is what you do if either one of them are even. And in this case, we only have cosine, and it's even, right? It says here, with this, we're going to use the half-angle identities or the power-reducing identities. And these are from pre-cal. And the two identities are written right there. And I'm going to write them up here just so you see them. Sine squared x equals 1 minus cosine 2x over 2. Anyone recognize that formula from pre-cal? We call this the half-angle or power-reducing formula. The thing that's good about this formula is that it allows you to take a trig function like sine that is being squared and rewrite it where there's no more squareds. But there's a give and a take. You lose the squared, but what do you gain? A double angle, right? You double the angle. So that's the formula. Now I have it written in a different way here. I have it written where I pull that 1/2 out of everything. Right? That's the same exact thing. Or you could split this into two fractions and go 1/2 minus 1/2 cosine 2x. All three of these are equivalent, right? They're all the same, and you can use any of those versions when you're doing this problem, right? There's another identity for cosine squared, and what's the difference between the two formulas? There's only one difference. Addition. If this was cosine squared x, this would become a plus, a plus, a plus. That's the only thing that changes. All right? So you ready to use those? Yeah? Come back to this. What does it say? If you have this even power, then you just use the formula. It doesn't tell you anything else. So let me try and rewrite this. I know that anytime I have a cosine squared, I can use this formula with pluses, right? So I need to first realize that I do have a cosine squared. I have a cosine squared beta t, what? Squared dt. Yes? That's what I have. Now, I can now replace cosine squared beta t with any of these. So I like to use this one. All right? The reason I like that one is because I can pull the 1/2 out at some point. So do you agree with this? I'm going to leave those formulas up there so you can refer to them. Y'all realize, since this is the only example I'm going to do, you'll realize I'm using this right here, right? That's the one I'm using, right there. Okay. So this becomes integral in parentheses. Ethan, have we talked today? Ethan? Okay. So use that formula. Tell me what this is going to become.
Kind of replacing
Oh, wait, I circled that one. That's not the one I want. Damn it. Sorry.
using the first.
I want this one. Sorry, I wanted this one. That's the one I like to use.
Okay.
Okay. So in that parentheses, what do you want me to write?
Putting 1/2
Okay, 1/2.
And starting another parenthesis.
Another parentheses.
1 plus cosine
1 plus cosine
of 2x.
of
2x. Or say
2 beta t. 2 beta t. Shit. Hold on. Okay, got to make sure I get my parentheses right there. 2 beta t is inside the cosine. 1 plus cosine is in parentheses. There's a 1/2 in front of that. All of that's being squared. Yes? So no matter what the argument is, right? The argument's the thing in the function. You're going to double that argument. So if it's beta t, it now becomes 2 beta t. All right, now let's actually do some cleaning up here. When you have something raised to the second power and you have multiplication, right? You can actually just square this one and square this one, right? So when I square 1/2, what do I get? 1/4. I'm going to pop that out of the integral now. So this becomes 1/4